Have you ever found yourself maybe sorting through photos, wishing you had a shortcut, like a super-powered way to automatically spot specific things in your images?
Or maybe, tag thousands of photos without having to manually sift through every single one.
Exactly. Imagine teaching a computer to literally see the world through your eyes. It sounds pretty futuristic,
It
right?
really does.
Yeah.
But today we're taking a deep dive into Azure AI Custom Vision. It's this uh, remarkably powerful image recognition service. Think of it as your personal machine learning assistant, basically.
Yeah, ready to tackle visual tasks. So today we're really digging into how you can build, deploy, and even fine-tune your very own custom image identification models.
Our mission here is to kind of unpack how you turn raw image data into real, actionable insights.
And the key thing is you don't need to be a machine learning guru yourself. We'll explore what it can do, the choices you'll face, and, follow that journey from just images to a working AI.
Right. And for this deep dive, we're drawing on a really comprehensive guide to implementing Azure AI Custom Vision. It lays out pretty much everything, from the basics right up to advanced deployment stuff.
Okay, so let's unpack this. Azure AI Custom Vision. What is it at its core?
So fundamentally, it's an image recognition service for building these custom models. Models that apply labels you define based on visual characteristics.
So you decide the labels, like classifying a whole picture or finding a specific thing in the picture.
Exactly. You specify your own labels, train the model, and it learns to detect them.
And how does it actually work? What's the magic behind it?
Well, the clever part is how it learns. You give the service images, some that have the thing you're looking for, some that don't.
Okay.
Then you label them, tag them. The machine learning algorithm takes that, trains itself, tests itself, or finds its understanding. It's iterative.
And I heard it's optimized for recognizing major differences pretty quickly.
That's a key point. It's great at spotting big visual distinctions fast. This really lowers the barrier to entry.
Meaning you can prototype quickly, even without massive data sets.
Precisely, which democratizes this tech, really. And the newer models, Image Analysis 4.0, they're particularly good at few-shot learning.
Few-shot learning, meaning?
Meaning you can often get surprisingly accurate models with less training data than you'd think, which is pretty amazing if you're just starting out or maybe you're working with niche images where getting lots of data is hard.
That sounds incredibly powerful. But okay, for someone starting out, how do they jump in? Is it all code or is there an easier way?
Oh, definitely not all code to begin with. The easiest way in is the Custom Vision web portal. It's customvision.ai.
Ah, a website,
Right.
visual interface.
Totally visual. You can upload, tag, train, test, all with clicks. It's fantastic for just exploring, getting hands-on.
But if you do need more control or want to automate things,
You've got options. There are SDKs, client libraries for different languages,
Right.
and a REST API for direct programmatic control.
right, for managing the whole model lifecycle through code.
Exactly. And it slots right into your existing Azure setup, so you get all the Azure security, compliance, scalability, the whole enterprise-grade package.
Okay, so you've decided to use it. You've maybe got some images. What's the first big fork in the road?
The first crucial decision is, do you want to classify the whole image or detect specific objects within it?
Classify versus detect. What's the difference in practice?
Okay, image classification. That's about applying one or more labels to the entire image. Think of it as a categorizer.
So like sorting photos into outdoor versus indoor, or product quality checks good versus defective.
Spot on. Or maybe classifying documents, invoice or receipt, or even medical scans healthy versus abnormal.
Let's take an example. Say sorting fruit.
Perfect. You'd train it with maybe 30 or more images each of whole apples, whole oranges, whole bananas.
Like 30 plus, is that a magic number?
It's the recommended minimum for a decent starting point. Give the model enough variety to learn properly. So you feed it a new image, and the output is simple. Apple, maybe 95% confidence.
Got it. So that's classification, categorizing the whole thing. But what if I need to know where the apple is in the picture?
Now you're talking object detection. That takes it a step further. It doesn't just say apple. It gives you the coordinates, the location of the apple in the image.
Coordinates, so like a box around it.
Exactly, a bounding box. And it can find multiple objects in one image and tell you where each one is.
So for, say, safety equipment, it wouldn't just say helmet present, it'd say helmet here with the box.
Precisely. You train it by drawing boxes around helmets and vests in your training images. The output for a new image might be safety helmet at coordinates, let's say, x 120, y 80, width 150, height 120, with maybe 92% confidence.
Wow. Okay. That's a different level. It's not just recognition, it's spatial understanding.
Really is. Think security, retail inventory on shelves, detailed quality control, finding specific anomalies in medical scans.
So just to summarize the choice, classification is kind of the simpler, faster route for general categories. Less data, maybe?
Generally, yes. Lower complexity, faster training, often needs a bit less data,
Hmm.
but still that 30 plus per tag minimum. Output is just labels for the whole image.
And detection is more complex, needs more careful labeling with those boxes, takes longer to train, but tells you where things are.
You nailed it. Detection is the locator. Higher complexity, more training time, needs more images usually, and very precise labeling.
Hmm.
But the output is labels with coordinates. Much richer spatial info.
What about the images themselves? Any technical rules, size limits, formats?
Yeah, there are some basics. The common formats like JPEG, PNG, GIF, TIFF, etc., under 20 megabytes per image.
Okay.
And dimensions need to be between 50 by 50 pixels and 16,000 by 16,000. So pretty flexible range.
But beyond the tech specs, what's really crucial for good training data?
Variety. Visual variety is absolutely essential.
Meaning, not just 50 identical shots.
Exactly. You can't just show it your product perfectly lit on a white background from one angle.
Right. The AI equivalent of only showing a kid pictures of your poodle and expecting them to recognize a bulldog.
Agrees. Perfect analogy. You need different camera angles, different lighting, various backgrounds, maybe different styles if applicable, individual items, groups of items, different sizes.
So it learns the concept of the object, not just that one specific photo setup.
Precisely. That's how you build a robust model that works in the real world.
Okay, so we've picked our path classification or detection and gathered diverse images. Next up, labeling. Teaching the AI to see. How does that work for classification? Seems simpler.
It is pretty straightforward. You just assign text tags to your images. Often easiest to upload images grouped by tag, like all your Apple pictures together.
But you can change them later if needed.
Oh yeah, you can always adjust tags for individual images. The key best practices are just consistency, trying to keep a balanced number of images per tag and using clear, unambiguous category names.
Avoid confusing labels.
Right. It's interesting how much that human input clear instruction matters for teaching the AI well.
Okay, but for object detection, it's more involved than just tags, right? You mentioned those bounding boxes.
Correct. You have to specify the region for each tagged object in each image. You do this using normalized coordinates.
Normalized coordinates, what does that mean? Left, top, width, height.
Exactly. But as percentages of the total image width and height. So the top left corner is always 0, 0, and the bottom right is 11, 1.
Ah, so it's relative. That makes sense. It means the label location works no matter the image resolution?
Precisely. It makes the labeling process much more portable and robust. The service handles converting those percentages to actual pixel coordinates later. It simplifies things a lot.
Okay, so drawing boxes. What if the object isn't perfectly framed, like part of it is hidden or cut off at the edge of the photo?
That's a really important point and something people often forget. If you want your detector to find partially hidden, occluded, or cut off truncated objects,
You have to show it examples like that.
you absolutely must include those kinds of examples in your training data. Otherwise, it only learns to recognize perfect whole objects.
Makes sense. Seems like a lot of drawing boxes, though. Are there any tools to speed this up?
Yes, thankfully. The Custom Vision web portal itself can actually suggest bounding boxes for common objects, which could be a huge time saver.
Oh, cool. Like auto-suggest for boxes.
Kind of, yeah. And for really large projects, you can use the COSIO format. It's a specific JSON standard for referencing images and all their labeling info, including the bounding boxes. Great for automating or outsourcing labeling at scale.
Okay, labeling done. We've taught the AI what to look for. Now, the actual training part, letting it learn, how does that work?
It's actually pretty simple, especially in the portal. You just hit the train button.
That's it.
Pretty much. The service takes all your labeled images and builds a model. For classification, it figures out the visual qualities of each tag. This usually takes just a few minutes.
A few minutes, wow. And you mentioned iterations?
Right. Every time you train, it creates a new iteration of your model with its own updated performance scores, so you can track improvement over time.
Are there different ways to train, like faster or slower options?
Yes, you typically choose between quick and advanced training. Quick
Mm.
is, well, quicker minutes, good for early tests, prototypes, uses less computation.
And advanced?
Advanced takes longer, potentially hours, but uses more sophisticated algorithms and usually gives better performance, better accuracy.
So start quick, then go advanced for refinement.
That's often a good workflow. You can also pick a domain like General, food, landmarks, retail. This just helps optimize the model for that specific type of image. You can change it later, too.
Can you automate this training part, like with the SDK?
Absolutely. The portal is great for visual workflow. Upload, tag, check you have 30-plus images per tag, hit train, pick quick, review. But for automation, the SDK is key.
So Python code could create the project, add tags, upload images, start training, and even monitor it.
Exactly. You can script the whole thing, kick off training, wait for it to finish, then automatically pull the results. Very powerful for CI/CD pipelines or regular retraining.
Okay, model trained. Now, how do we know if it's actually any good? How do you measure success?
Evaluation is crucial. There are three main metrics you'll look at. First is precision.
Precision, that's about accuracy.
It's about accuracy of the positive predictions. Ask, of all the times the model said it found an apple, how many times was it actually an apple? If it identified 100 things as apples and 99 were correct, that's 99% precision. High precision means few false positives.
Okay, so precision is don't guess wrong. What's the next one?
Next is recall. This is about finding everything you're supposed to find. Ask, of all the actual apples in the data set, how many did the model correctly identify? If there were 100 real apples and it found 80, recall is 80%. High recall means few false negatives.
Got it. Precision, few false alarms, recall, don't miss things. And there was a third one, MAP.
Right, mean average precision, MAP.
Mhm.
This is kind of the overall score, especially vital for object detection. It considers both precision and recall across different confidence levels.
And for object detection, it also cares about where the box is, right?
Exactly. It incorporates something called intersection over union, IOU. IOU measures how much the predicted bounding box overlaps with the actual object's box. A high MAP means the model is good at both identifying and locating objects accurately.
So MAP is like the final grade, factoring in both what's and where.
That's a great way to think about it. And you'll often see MAP calculated at different IOU thresholds, like MAP at 50% IOU or MAP at 75% AIU, showing performance at different levels of location accuracy strictness.
And there's that probability threshold slider too. How does adjusting that affect precision and recall?
Yes, the threshold. It defaults to 50%. If you slide it higher, you demand more confidence from the model. You'll get higher precision, fewer false positives, but likely lower recall. You might miss some real ones.
And lower threshold?
Lower threshold means the model reports things it's less sure about.
Yeah.
You get higher recall, catch more real ones, but likely lower precision, more false positives. You tune this based on your application's needs. Is it worse to miss something or worse to have a false alarm?
So finding the right balance for your specific use case. If a real system had, say, MAP over 85% and precision recall over 80%, this is pretty good.
Those are definitely strong numbers, yeah. Indicates a potentially solid model, but you always want to test it on completely new, unseen data too, just to be sure. Success really depends on the specific KPIs, key performance indicators, you set for your project.
Okay, model, trained, evaluated, looking good. Time to actually use it. How do you publish it?
Publishing is basically making a specific trained iteration available via the prediction API. You go into the portal, pick your iteration, hit publish, and give it a name.
And that makes it live.
Yep, a published label appears next to it. It's now accessible using your Custom Vision Azure Resources prediction endpoint.
And you need some keys or URLs to call it.
Correct. When you publish, you get a dialog box with the crucial info.
Yeah.
The prediction URL, that's the API endpoint, a prediction key for authentication, your project ID, and the published model name you just assigned.
Keep those safe. And you can do this publishing step via the SDK too, I assume.
Absolutely. Portal is easy. Performance tab, select iteration, publish, name it, pick prediction resource, done. SDK is just a command like trainer.publish iteration, perfect for automation.
And since you have iterations, how do you manage different versions?
Good question. Each training run creates a new iteration with a unique ID, its metrics, timestamp, etc. Best practice is to use descriptive names, document the changes you made for that iteration, keep track of performance baselines, and definitely have a plan for rolling back to an older version if needed. Version management is key in production.
All right, published. Now the really fun part. Consuming the model, sending it new images and getting predictions. How does that work in code?
You use the prediction API client. In Python, for instance, you'd use Custom Vision Prediction Client. You authenticate with your key and endpoint.
And then just send an image file.
Pretty much. For classification, you send the image, and the response gives you the predicted tags and their probabilities.
And for object detection.
Similar process, but the response includes that extra bounding box data, the coordinates for each detected object, along with the tag and probability. You see the locator in action.
So the response is typically JSON listing the prediction.
Exactly. An array of predictions, each with probability, tag name, and for detection, the bounding box details.
How do people usually integrate this? Real-time batches.
Both are common. You can set up real-time processing, maybe taking images from a stream, converting them, getting predictions quickly, and filtering by confidence.
Filtering, like only acting on predictions above 90% confident.
Precisely. That's using the confidence thresholding we talked about. It's super practical. Or for large volumes, you can do batch processing, sending multiple images efficiently.
Is there anything else like advanced options when predicting?
One important one is the no store option. There are specific methods like predict image with no store that tell the service not to save the image you sent for prediction.
Why would you do that?
Privacy or compliance, mainly. Normally, Custom Vision keeps prediction images temporarily, potentially to help you improve the model later by adding them to training. But if the images are sensitive, with no store ensures they aren't retained by the service.
Got it. Okay, we've covered the portal quite a bit. Let's shift fully to the code-first approach with SDKs. How do you get started there?
First step is installing the SDK, like pip install Azure Cognitive Services Vision Custom Vision for Python. Then you set up authentication using your API keys and endpoint for both the training and prediction clients.
And then you can manage the whole lifecycle, create projects, tags.
The entire lifecycle. You can write code to, 1, create a new project, pick its domain, specify classification type. 2, create all your tags programmatically.
3, upload images. How does that work with tags or boxes?
For classification, you upload images in batches, up to 64 at a time, along with their tags. You need good error handling here for any failures. For object detection, you upload images and provide the list of bounding box regions for each image.
Okay, data uploaded. 4, training.
Yep. Programmatically start training using train project and, crucially, monitor its status using git iteration until it's marked completed. Then you can fetch the performance metrics using git iteration performance.
That's slick. Then 5, publish automatically.
Exactly. Use publish iteration, give it a name, and specify the prediction resource ID. Then you can retrieve the prediction endpoint details needed to actually use the model.
So you could literally script an entire project, say, that fruit detector example, end to end.
Absolutely. Create project, create apple, banana tags, upload data with boxes if detecting, train, publish, test prediction, all automated. It shows the real power of the SDK.
Error handling must be critical in automated scripts like that.
Oh, absolutely vital.
Right.
Robust image upload logic with retries, checking file sizes are under 20 MB. And the performance monitoring can be quite detailed too.
How detailed.
You can get per tag precision and recall, and sometimes even recommendations from the service itself based on the metrics. Like, consider adding more diverse negative samples if performance isn't great on certain things.
The system actually suggests improvements. That's cool.
Yeah, it can be really helpful for iterative development.
And for managing models and production code, beyond just iterations.
A common pattern is building a sort of custom vision model manager class. It can handle registering new model versions, deploying them, comparing performance, maybe even implementing fallback logic.
Fallback logic, like if the main model isn't confident.
Exactly. If the primary model gives a low confidence score, the manager could automatically call a secondary, perhaps older but reliable, model as a backup, essential for robust systems.
How does Custom Vision play with other Azure services?
Very well. You can easily integrate it into Azure functions for serverless real-time image processing triggered by HTTP requests, for example.
Or processing lots of images stored somewhere.
Right, you can use it with Azure Blob Storage for batch processing. Use something like Python's thread pool executor to process images from blobs in parallel for high throughput.
Security is always a big concern. How do you handle keys securely?
Best practice is not to hardcode keys. Use Azure Key Vault to store your training key, prediction key, and endpoint. Then your code uses default as your credential to securely fetch them at runtime.
And logging for audits.
Definitely set up robust audit logging.
Yeah.
Capture timestamps, the operation type, training, prediction, image IDs if relevant, prediction results, everything you need for compliance and traceability.
Let's make this more concrete. Real-world use cases. Manufacturing quality control seems like a classic.
It's a perfect fit. You set up tags like good, defective, maybe specifics like scratched, dented.
Yeah.
The key, again, is training data, variety, different lighting, angles, backgrounds, covering all the defect types.
And the benefit is faster, more consistent inspection.
Exactly. Automating the routine checks frees up human inspectors for the really complex edge cases.
What about retail, inventory management?
Huge potential there. Cameras monitoring shelves, models trained to recognize products, detect out-of-stock gaps, even spot misplaced items.
So it's not just counting, it's understanding the shelf layout.
Right. You could configure detection frequency, set confidence thresholds for alerts, integrate with inventory systems. Imagine automatically knowing when premium products aren't facing forward. It optimizes stocking and reduces lost sales.
That could genuinely change how stores operate. And healthcare? Medical imaging?
A very impactful area. Classifying scans normal, abnormal, requires review to help radiologists prioritize.
But compliance must be extremely strict there.
Paramount. You need things like strong data encryption, AES 2526, full audit logs, strict role-based access control for patient data privacy, and robust data retention policies, often years long. It's about empowering clinicians with a reliable second opinion tool while adhering to rigorous standards.
Okay, last big topic. Optimization. Keeping things efficient and cost-effective. How do you optimize training?
It mostly comes back to data quality. Validate your data, check image distribution across tags, make sure you have enough samples, that 30+ minimum, and watch out for dataset imbalance. If one tag has way fewer images, add more for that tag.
Quality in, quality out, and managing the actual cost.
Several strategies. For training, use quick training for early tests, upload images in batches, delete old, unused iterations.
And for prediction costs,
Cache results for frequently analyzed images if possible. Use appropriate confidence thresholds. Don't pay for predictions you won't use. Consider setting prediction quotas if budget is tight.
what about storage costs for the images?
Compress images before uploading, try to remove duplicate training images, and archive or delete old project data you no longer need. It's about being mindful across the whole life cycle.
So wrapping up, Azure AI Custom Vision really offers a powerful yet accessible way to build custom image recognition.
Yeah, the barrier to entry is relatively low. You don't need deep ML expertise to start. You get flexibility with the web portal or the SDK.
And it's built for real-world use, enterprise security, scalability, ready for production. Plus, it's cost-effective if you manage it smartly.
Definitely. Success really boils down to a few things. Quality training data is number one. Then that iterative process train, test, improve, repeat, proper evaluation, and thoughtful deployment.
So what are the next steps for someone listening?
I'd say start with the web portal, get your hands dirty, prototype quickly. Then, for serious development or automation, move to the SDK.
And keep monitoring performance, plan for updates.
Exactly. Treat it like any other software component that needs ongoing maintenance and improvement.
It really feels like custom vision democratizes computer vision, making this advanced tech usable for so many more people and businesses.
It truly does, which leads to a final thought.
Yeah.
As you think about this, consider what overlooked visual task, maybe in your work, your industry, or even just daily life, could be transformed if a computer could genuinely see and understand it through a lens you trained yourself. What insights could you unlock?